Okay, a linear congruence is a congruence that is similar to a modular congruence, but now we're going to add an x. So we say ax is congruent to b mod n, and we have that a and b are integers, and n is a positive integer. And this is a linear congruence. And there's multiple ways to solve linear congruences, and the way that I'm going to show you uses a few theorems. Your book shows you a different way that you can go and look at and explore, but I'm going to show you this way using two different theorems. So the first theorem, Theorem One, is that if a and n are positive integers greater than 1, with n greater than 1, and a and n are relatively prime, then there is an inverse, which we're going to denote a bar, such that a times a bar is equivalent to a bar a, which is equivalent to 1 mod n. And our a bar is going to be a positive integer less than n. Okay, this is also unique mod n. So a is this, sorry, and a bar is unique. All right. If you look at the online notes, I give the proof of this. So first we have to prove that the inverse exists. There is an inverse, so we prove that that's true. And then we also prove that it's unique. And you can go look at the printed notes and ask me questions about that if you have some. The other theorem that we need for this to help solve linear congruences, Theorem Two states that for all n and k that are positive integers with n greater than k, then there's some na minus k mod n. Oops, not mod 7, sorry. That is equivalent to negative k mod n. And of course this is true because this is a multiple of n, so this mod n is just going to be 0, so that's going to cancel out. So this one, fairly trivial. And we're going to use these down here to find multiplicative inverses. So we're going to go back and use the idea of Theorem 1 to find our multiplicative inverse, and then we're going to use that to help us solve linear congruences. And we'll look at those in the upcoming videos.